Hello and welcome back to MEC 416/816 Engineering Acoustics. In this video, we're going to continue our discussion about reflection and transmission, and we're specifically going to focus on transmission from one fluid to another with normal incidence. To this end, we're going to consider two fluids. We're going to just draw the boundary between them as a vertical line here. On the left, we're going to have fluid 1. On the right, we'll have fluid 2. We said before that the specific acoustic or characteristic acoustic impedance R1 will be equal to rho 1 times C1, and then on the other side we'll have R2 is equal to rho 2 times C2. We'll have some incident wave coming towards the boundary. We'll say that is P over bar I. And then we're going to have some transmitted wave, which we'll say is P over bar T. And then lastly, we're going to have a reflected wave off that boundary, which we'll say is P over bar R. And then at the boundary, I'm going to have to redraw this boundary. Actually, we'll just leave it as. But at the boundary, we're saying X is equal to 0. So again, we're considering plane waves propagating here, and they're propagating in a single direction, or at least we've aligned the coordinate system to be such that the X direction coincides with the direction of propagation. From here, we're going to expand, we're going to say that the incident wave is some kind of harmonic traveling wave with an amplitude of capital P sub I here. This is not a vector, that's a capital P, which when striking the boundary will generate a reflected wave, that PR, and PR over bar will be equal to some complex amplitude capital P sub R over bar times e to the j omega t plus k x in this case. So we now have a wave propagating in the other direction, so we have to use a plus in there rather than a minus sign. And now for the transmitted wave, we'll have Pt over bar is equal to big P sub t over bar times e to the j. And in fact, what I left out here is that this should be a K1. And in the transmitted wave, we're going to have omega t minus K2 times x. Okay, so since the fluids are lossless, the waves must have the same frequency. That is that omega depends on the distant source and not the fluids. It does not change because of the fluids. But the wave numbers themselves, K1 and K2, those are dependent on the fluids. And specifically, we can say that K1 is equal to omega divided by C1, and K2 is equal to omega divided by C2. So that you can see how they now depend on that. They are dependent through the speed of sound. Okay, so at our boundary where the two media meet, there are two boundary conditions that must be satisfied for all times. So first, the acoustic pressures on both sides of the boundary must be equal. So the acoustic pressures on both sides of the boundary must be equal. Which ends up being a balance of forces. And second, the second condition is that the normal components of the fluid particle velocity on both sides of the boundary must be equal. So the normal components of the fluid particle velocity on both sides of the boundary must be equal. Okay, so condition 1 was a balance of forces, and then condition 2 requires that the two fluids remain in contact. In fact, let's go ahead and write this down. So condition 1 requires that there is no net force, let's say. Requires that there is no net force acting on the massless plane separating the fluids. No net force acting on the massless plane separating the fluids. Of course, there can't be any force acting on it, otherwise that plane would then move. And it's massless, which means that it cannot support any movement. And then condition 2 requires that the fluids remain in contact at all times. So there's no gaps or vacuums opening up between the two fluids. They're always touching each other. So condition 2 requires that the two fluids remain in contact at all times. Okay, so mathematically, these conditions are that Pi plus PR equals PT at x equals 0. So at the boundary, at x equals 0, the pressure on the left-hand side, if we just scroll up momentarily, the pressure on the left side, Pi plus PR, must be equal to the pressure on the right side, which is PT in this case. That's our first boundary condition. And then the second boundary condition is that Ui over bar plus UR over bar must be equal to UT over bar, where these are just the normal components to that boundary. And again, this is true at x equals 0. And these are then statements of continuity of that specific acoustic impedance across the boundary. All right, so since a plane wave has the following property, and let me just correct this here. We'll drag this on over. So plane wave, let me drag that. So since the plane wave has the following property, that the pressure divided by the fluid particle velocity is equal to plus or minus the characteristic acoustic impedance. And here, this plus or minus depends on the direction of propagation. Depends on the direction of propagation. And in this case, for forward, you'll use a plus sign. For backwards propagation, you'll use a minus sign. Okay. So from here we can divide 7 by 9. Those are our boundary conditions. We'll divide 7 by 8 actually. And what we'll get on the right-hand side is P over bar I plus, let me write that I as a subscript, plus PR over bar divided by UI over bar plus UR over bar is equal to PT over bar divided by UT over bar. And this is true only at x equals 0. This is not true anywhere else. From here, we can then use equation 9 to simplify. Simply we'll plug in what we have in equation 9 and simplify and find then that R1 times the fraction Pi, let me rewrite that a little bit neater. we'll have pi over bar plus pr over bar divided by pi over bar minus pr over bar is going to be equal to R2. So what we did here, I'm going to draw with the laser, is we took the relationship in equation 9 that I'm circling now. We took that relationship for pi, pr, for u. We used this relationship. We multiplied both sides by u, and then we divided by r. So in green here, we'll add, or actually we'll use purple. So we'll put it here. So this means that u over bar is equal to p over bar divided by, in fact, let's bring that plus or minus back. So is equal to then plus or minus p over bar divided by r. And we then took that and we're plugging this relationship in for ui and then also for ur, and then after that we ut. So we would have pt over r2, pi over r1, pi over r1 as well. And then we can pull the r1 out and simplify as shown here. And again, this is still only true at x equals 0. At x equals 0. It's not true anywhere else. And so just to kind of summarize, note that ui over bar is equal to, in this case, plus pi over r1, ur is equal to minus pr over r1, and ut over bar is equal to pt over r2. Okay, so from here what we're going to do is we're going to multiply both sides by pi minus pr. This will eliminate it in the denominator on the right, on the left-hand side. We are then going to group up terms in front of the pi and terms in front of the pr. We're then going to isolate and manipulate, so subtract or add things on each side, such that on one side of the equation we have pi and things multiplied by it, and on the other side we have pr plus things multiplied by it. We will then divide and produce the quantity PR over PI. And doing so then results in the following behavior. And in fact, for a mini homework, and let's say this should be due on, let's say on March 26th in class, or a class after that if not that day, you should go through and do these bulleted point steps and demonstrate that indeed we can go from equation 11 to equation 12. Okay, so in this case, R is going to be equal to the quantity lowercase r2 minus r1 over r2 plus r1. Or another way to write this is r2 divided by r1 minus 1 divided by r2 over r1 minus 1. And something you should note is that the reflection coefficient is always real for normal incidence of two fluids. If you have three fluids, then it's no longer going to be real. Or if you have more than, let's just say more than two, you could have 4 or 5 or whatever. In all those cases, it's not going to be real. Okay, so let's go back and consider now equation 7. Let me, in fact, we have it written right here. And what we're going to do is we're going to divide both sides here by pi. And what we'll get first is, the first term will get a 1 plus pr over bar divided by pi over bar, and then equal to pt over bar divided by pi over bar. which clearly ends up being 1 plus r is equal to t. So again, this is our transmission, this is our reflection coefficient, and so we find that the transmission coefficient is equal to 1 plus r, and then this then leads to the transmission coefficient t being equal to 2r2 divided by the quantity r2 plus r1, which might also be shown to be equal to the quantity 2r2 over r1 divided by r2 over r1 plus 1. The reason why we give the second form is that sometimes you'll get you'll know the ratio of the characteristic acoustic impedances, but you won't know what they are individually. Okay, so what we're going to do now is study what happens under different conditions and different types of reflection coefficients. So first of all, when big R is greater than 1, or big R is greater than 0 when little r is less than r2. In this case, the reflected wave remains in phase with the incident wave. So reflected wave is in phase with the incident wave. Big R is less than 0 when R1 is greater than R2. And in this case, the reflected wave becomes out of phase with the incident wave. Okay, then lastly, when R is equal to 0, when R1 is equal to R2. So that might mean that there are different fluids, but if they have the same characteristic acoustic impedances, there will be no reflection. So in this case, there is no reflected wave and complete transmission. So we have complete transmission. All right, so that transmitted coefficient is always going to be positive, and the transmitted waves are always going to be in phase with the incident wave for normal incidence for two fluids. Okay, we're now going to consider what happens in the limit of R1 over R2 as it approaches 0 and as it approaches infinity. And so what you should do is pause the video and try and think about what happens physically with each of these cases. Try and think of what this means physically for the wave in terms of both, first what happens to the reflection and transmission coefficients, and then what is physically going to happen to the wave. Take a moment, pause the video, and think through this. Okay, welcome back. So we're going to now go through what happens in each of these limits. So in the limit as R1 over R2 approaches 0, first the reflected wave is going to have the same phase and amplitude as the incident wave. So the reflected wave has the same phase and amplitude as the incident wave. So this is a case where R1 is not 0, but R2 is very, very large. So large that this quantity is approaching 0, meaning that their density and speed of sound and so forth is extremely high in the second fluid. So in this case, again, the reflected wave is going to have the same phase and amplitude as that incident wave. meaning that there's going to be a complete reflection. That doesn't mean that the transmitted wave is zero, though. And in fact, the transmitted wave is going to have a pressure amplitude that is twice that of the incident wave. And this is something you can show using the reflection coefficient or the transmission coefficient that we discussed. In fact, you should take a moment and go through that and see. So the transmitted wave has a pressure amplitude twice that of the incident wave. Twice that of the incident wave. Third, the normal particle velocity at that boundary is going to be zero. At the boundary is zero. So this is what is known as a rigid boundary condition. This is the fluid equivalent of a rigid boundary. And one thing that is different here compared to the rigid boundary for elastic media is that here the velocity is equal to zero, the fluid particle velocity, not the displacement. The fluid particle velocity is equal to zero. You could then say that the displacement needs to be a constant as a result of that, normal to the boundary. But we're going to focus really only on using the fluid particle velocity. Okay. So, if you haven't, take a moment and pause the video and now think about what happens in the opposite limit. And then we'll discuss when you come back. Okay, so now in the limit as r1 over r2 goes to infinity, and in this case r2 is becoming extremely small, such that this blows up to infinity, or in this case, the reflective amplitude is going to have the same amplitude as the incident wave, but it's going to be out of phase. So we'll just say the reflected wave has the same amplitude, as the incident wave, but is out of phase. In this case, the transmitted wave is going to have zero amplitude. This is the case where there is no transmitted wave. So the transmitted wave has zero amplitude. Meaning that there is no transmitted wave. Third, the pressure at the boundary is going to be zero. The pressure at the boundary is zero. And this is called a pressure release boundary. Because that pressure is zero, therefore it's a pressure release. Okay, so in the next chapter, in chapter 5 of OS, which is chapter 9 in the book, we are going to consider boundary conditions for when we do separation of variables and find solutions for standing waves, but I just want to briefly talk about what these boundary conditions are. So when we talk about a rigid boundary, we are thinking about something like a wall, some solid object where the wave will just bounce off of it. You could also think about the boundary between water and air, because water is so much more dense than air. You could consider that to be a rigid boundary. That is one option. If you're thinking about the wave propagating in air and then hitting the water and bouncing off of it. For a pressure release boundary, you can think of something like, for example, if we're considering a wave propagating in water, you could consider if a surface of that water is being exposed to the atmosphere, you can consider that to be a pressure release boundary, meaning that the pressure in the air above the water, like in the ocean, for example, is much lower than the pressure in the water. And so you could choose to model that as a pressure release boundary if you wanted. Another option would be if we wanted to think about the atmosphere and space, and if we were to assume that there is a discrete boundary between when the atmosphere ends and when vacuum of space begins, which there isn't, but if we wanted to assume that, let's say, you could then model that as a pressure release boundary as well, because there will be a sudden change in the pressure. If you wanted to, you could also, for water-air boundary, you could choose not to consider that as a pressure release or a rigid boundary, depending on what you're doing. But we'll deal with these more in the next chapter, in our chapter 5. Thank you very much for listening.